Good morning, everybody. So it's a pleasure to have Lionel Messi, Lionel Mason, starting with the first talk. So it's going to be about four-dimensional Chern Simons to Hitchin self-duality equations on the Riemann surface.
Well, thank you very much for associating me with such greatness. I believe that today the great Lionel Messi is going to destroy the UK, but we'll see. Well, I should be loyal to my country. Sorry, England, not the UK. Anyway, so I'd like to thank the organisers for inviting me here, and I feel to a certain extent like I'm coming back home to a world of integrability now, having been outside of it for sort of more than 2 decades. So what I want to talk about today is joint work with Roland Bittelstern and Farouk Mazafian, and I want to sort of go back to start off with some 30 years to why it is that I'm sort of coming back home, really to ideas that were in a book that I wrote with Nick Woodhouse 30 years ago, Self-Duality, Integrability, and Twistor Theory. This book was sort of based on various observations that really a number of people were making in the 80s, that many or indeed most key integral systems arise as symmetry reductions of the four-dimensional self-duality equations. And so a small catalogue of those were developed by people like Nigel Hitchin, Richard Ward, and friends. And I came in slightly late to the game with showing that the key examples, nonlinear Schrödinger and Korteweg de Vries, were also symmetry reductions in a completely canonical way. And the significance of that is not just to tie it in with sort of gauge theory and four-dimensional sort of physics, but also because at that period, the self-duality equations of 4 dimensions have been shown to be soluble using ideas from twistor theory. So the self-dual Yang-Mills equations have a construction for their, I use the word in inverted commas, complete solution by Richard Ward using, and I'll have a slide on this later, using data on twistor space, which is a 3-dimensional complex manifold, and so you can write down data on twistor space, which is freely prescribable, and use that to construct the general solution. And there were similar ideas for the self-dual Einstein equation. And so this led to a program that Nick Woodhouse and I followed in this book, which was to classify the integral systems in terms of their reductions from the self-duality equations in 4 dimensions, and to derive the theory of those equations via reductions of the twistor correspondence. So that logo there is a sort of picture of a twistor that Roger Penrose likes to draw. And so this was sort of successful as far as it goes. Yeah, there we go. So yeah, just to explain sort of what I mean by some of that, though. So let's just write down what the Yang-Mills equations are in 4 dimensions. So here I'm really going to think about it in a bit more of a Euclidean context, and as if the 4 dimensions is really C2, but thought of in a real way. So with complex coordinates W and W bar, I equals 1 and 2. And if you do that, then self-dual Yang-Mills is a theory of a gauge connection on a bundle over Euclidean 4-dimensional space, or C2, with its choice of a background complex structure. And the choice of the background complex structure allows you to sort of see that the self-duality equations tells you something about the connection. It tells you that certain components of the curvature vanish. So, for example, this connection is associated with a holomorphic connection in this complex structure, and that the Kähler form of this representation of the metric is wedged against the curvature vanishes. But this choice of complex structure wasn't very special. You can put a parameter in there, Z, which rotates the complex structure, and this integrability embodied in F02 and F20 being 0 applies equally to any other choice of complex structure. And this gives rise to a lax pair. So this Z is now a complex parameter on the Riemann sphere. And this integrability somehow tells you that these three equations here are sufficient to show that the lax pair commutes, and vice versa. So it's two ways. If this commutes, then we get these three self-duality equations. So this we can exploit the integrability to solve two of these equations directly. So famously, connections on Hermitian vector bundles. So if you assume that this is an SUN connection, there's naturally a Hermitian structure, and these two equations here, F02 equals 0, F20. Well, F02 equals 0 tells you you can find a holomorphic frame, and in that holomorphic frame, you can that the Hermitian form is no longer going to be sort of trivial, and it can be represented by a matrix that's become known as Yang's J matrix. And so in the holomorphic gauge, AI is 0, and A tilde I is determined in terms of J. So this is Chern's unique connection on a holomorphic vector bundle associated with the Hermitian metric. And then this equation reduces to the remaining equation here. So you've really solved these two equations directly, and the remaining equation here gives rise to what's known as the Yang's J matrix equation, or in more modern terms, it's a four-dimensional WZW model, because these aren't symmetrized derivatives. This is d bar J inverse dj equals 0. If it's symmetrized, then it would be a harmonic map, but it has a skew part. It's got a WZW term. Okay, so these are what the self-dual Yang-Mills equations look like in 4 dimensions. And to give you just a brief flavor. Oh yes, hi. Hey, I feel that. Sorry, where? Sorry, A star has turned into A tilde. Yeah, sorry. So the A star here, this would have been something you express in a Hermitian frame. So A star is the Hermitian conjugate of A, but of course now we're in a non-Hermitian frame. So you have to go to a non-Hermitian frame to set AI equal to 0, and then this A star is no longer the Hermitian conjugate of A. And so I've had to sort of relabel it A tilde. So I could have sort of done A tilde all along, and then, yeah, but yeah, thank you for that. Okay, so those are the self-dual Yang-Mills equations. And just very briefly, how do they fit into a twistor correspondence? Well, these twistor correspondences arise from a double vibration. So it's sort of simple to see where it might come from. So here, space-time is this R4 or C2 with these complex coordinates WI. And we've also had to give a life to the spectral parameter Z, which is which plays a role in the lax pair. And the lax pair has an underlying vector field given by d by dw bar I minus z d by dwi. And so on this space up here, we can sort of quotient by this vector field. As I've stated it, in fact, this isn't really a quotient. This actually so if everything was complexified here, this would be a quotient, but these are complex vector fields. So they actually define a complex structure on PT. And and as a complex manifold, so really this is an identification, a one-to-one identification. As a complex manifold, this PT is complex projective 3 space minus a line. So you can forget the fact that it's a Cartesian product of R4 across the Riemann sphere, and it is just a region in complex projective 3 space. What Richard Ward's correspondence does is it says that if you have a self-dual field on space-time here, then that corresponds to a holomorphic vector bundle on PT. And the version I'm giving here is really the Atiyah Hitchin Singer version, in which it's virtually trivial, because what you're saying is that the PT is equal to n cross CP1, R4 cross CP1, and the integrability of the lax pair is the integrability of the complex structure, is giving a lift of this complex structure to the bundle. And in that Atiyah Hitchin Singer world, then the lax pair is telling you that you have a holomorphic vector bundle on PT. If you were to complexify, you could define the fibers of the vector bundle over a point in PT as being the space of solutions to the lax pair on the corresponding integral surfaces of this pair of vector fields. And then that gives rise to a completely different description. So here, we obviously have the description in terms of a gauge connection, but over here, because it's a holomorphic vector bundle, you have this sort of famous check description where you trivialize. Sorry, I don't know if anybody's going to be able to see the board, but you imagine you trivialize PT with two open sets, U1, U2, and you can trivialize the vector bundle on both open sets, and the bundle is defined by a patching function, which I'll call P up there, on the overlap between these two open sets. And it's not trivial to go from such a patching function on twistor space back to the solution on space-time. You have to solve what's essentially a Riemann-Hilbert problem to do so. And in some sense, this Riemann-Hilbert problem is a familiar feature of treatments of integral systems of many types. It's a part of the inverse scattering problem for your favorite two-dimensional equations like the quatermative Riesz or nonlinear Schrödinger and so on. Okay, so then this gives you a kind of masterpiece of theory at which could then be applied to all of the symmetry reductions. And so, as I was saying in the first slide, that if you can take the self-dual equations in 4 dimensions as a master theory, and then you can study the reductions down to lower dimensions. And there's a similar story for gravity, which I won't go into. But for self-dual Yang-Mills, it was already well known in the 70s that, for example, the Bogomolny equations, the monopole equations, are naturally arise in the BPS limit, naturally arise as symmetry reductions of the self-duality equations. And then there's the Ward and Manikoff-Sakharov-Karl models. I saw Lewis had a nice poster on those yesterday. And then going down to 2 dimensions, so you can take the J matrix form, or you can take other ways of putting the connection into some normal form under symmetry reduction. One of the most famous reductions are the Ernst equations in 2 dimensions, which are the equations which characterize stationary axisymmetric solutions to the Einstein equations. Lots of sigma models, total field theories, nonlinear Schrödinger, quatermative Riesz, and so on and so on. And in fact, this talk is going to focus on the Hitchin equations, which I'll come to later. And going down to the Pan-Levitt equations, Garnier systems, Euler and Manikoff's tops. So our book is sort of filled with tables. So it's full of tables of different symmetries you can impose on the self-dual Yang-Mills equations. In 4 dimensions, the equations are conformally invariant, so you have a lot of symmetries to choose from. And so you have the choices of symmetries, but you also have the choices of gauge fixing. The J matrix is one, and there are various other ways you can present the connection in terms of potentials or other things. So this was the story. Starting with self-dual gravity, you very naturally ended up with dispersionless versions of KP. So the symmetry reductions there again come down in a natural way to various equations in 3, 2, and 1 dimensions. Okay, so that was the first half of the book, and then the second half of the book was then trying to develop the theory of those equations from the symmetry reductions. You would have some version of this Ward correspondence for each equation. But one of the issues was, in fact, that in some cases you learn something, but in other cases people already knew how to do stuff. So we could say new things about certain families of equations. Even in 2 dimensions, if the reduction was not too degenerate, so the Ernst equations are stationary and axisymmetric, and so the twistor construction reduces in a smooth way to 2 dimensions. But for just under 2 translations, the reductions are actually singular. So the twistor theory had to be treated in a very piecemeal way. And that was sort of awkward. So we could embed the standard theory from your favorite textbooks. In those days, there was Fadiethin Takhtajan and Abdovitz and Clarkson and various other books like that. You could embed it into the twistor framework, but you couldn't really sort of derive it properly. And the other issue in the book was that Hamiltonian structures weren't well treated. And most people here will probably agree that Hamiltonian structures are pivotal to one's understanding of integrable systems. Certainly the concept of complete integrability comes from the Liouville image of having infinitely many conserved quantities in involution and such like. So, so those issues somehow took a long time to be resolved. I think already back in the 90s, we were sort of aware that Chern Simons might have to provide a kind of paradigm for the theory that underpins the twistor space law, because you are talking about integrability of a complex structure. So some version of holomorphic Chern Simons should work. This was expressed for by Whistle in 2003 quite nicely in the context of twistor string theory. So when he was trying to write down effective field theories of what was going on with the twistor string, he treated the self-dual sector as a BF theory. So so the F being the integrability condition on the complex structure, and then the B being, as it turns out, having a nice interpretation as so the F gives you the self-dual sector, and the B then gives you the anti-self-dual sector. So that was very nice, and that drove the twistor applications to amplitudes for well, really for the subsequent periods, 2 decades. But if you're just interested in the integrability, BF theories, Lagrange multiplier theories, they don't really encapsulate the self-dual sector on its own. You're adding on extra degrees of freedom, the anti-self-dual part of the field. And there was a breakthrough with the work of Costello and Yamazaki just in the 2-dimensional world by introducing Chern. So you really want a Chern Simons theory. So in fact, what Witten did was he showed that the supersymmetric Yang-Mills theory had a self-dual sector which could be treated as super Chern Simons, but we really want a bosonic Chern Simons theory. And Costello and Yamazaki already introduced that in two-dimensional context, mostly for sigma models or principal Kara models. The and I guess Biddleson and Skinner sort of saw the relevance of that approach to the four-dimensional story, and so that they could see that this could be lifted to the full four-dimensional story, and then showed how you could reduce it down to get the four-dimensional Chern Simons story as a partly complex thing. So just to give a bit more detail on that, so as I was saying, self-duality Mills corresponds to holomorphic vector bundles on the twistor space, then, which is, as I say, a region in complex projective 3 space. And so it's already the case that the Lax pair is giving you a D-bar operator. And so just more generally, we could give a Dolbeault description of the vector bundle over twistor space. And then the field equation is simply that F02 vanishes. So that's the anti-holomorphic part of the curvature should vanish, and that gives you the integrability. And this really is just the Lax pair. And so that arises from the familiar Chern Simons action. I haven't written out the Chern Simons action. I hope everyone can remember it as trace ADA plus 2/3 A cubed. But its principal property is that its variation is the curvature. And then that curvature gets wedged against the holomorphic volume form. And so you only learn that the anti-holomorphic part of F vanishes. Okay, so we sort of half knew this in the 90s. I mean, this is something that, but what we didn't know how to deal with was the fact that the twistor space is not Calabi-Yau. So in fact, the canonical bundle has degree -4, and that means there's any choice of holomorphic volume form must have 4 poles up to multiplicity. So you could have 2 double poles, for example, or 4 separate poles, as you like. And I guess in the 4D Chern Simons story, Costello, Yamazaki, and Witten had shown how to manage these poles. I think this is what we didn't know how to do before. And I'll go into more details about that shortly. And so they learnt how to introduce boundary conditions so that this action made sense at the poles. And with that, Biddleson and Skinner were able to lift the 4D Chern Simons story to a 6D holomorphic Chern Simons story, in which they mostly dealt with a case where the form here has 2 double poles. And if you do 2 double poles in omega, then what you find is you land on Yang's equation naturally. So the double poles have the effect of choosing the holomorphic frame that I told you about in the first slide, and expressing things in terms of a Yang's J matrix, or the 4D WZW model. And so in this world, then, if you want to perform the symmetry reduction under 2 translations, there isn't actually a problem. This space is R4 across the Riemann sphere. And if you want to impose 2 symmetries, then you can get rid of 2 of the R4 directions as you like. And you're getting R2 across the Riemann sphere. And that was the world of Chern Simons. The R2 is what's known as the topological plane. The Riemann sphere is the holomorphic plane. This omega descends to a holomorphic 1 form. and this can be used to study. So four-dimensional WZW models then sort of reduced down to 2D sigma models. And later we'll see that sort of that there are some versions which will reduce to the Hitchin equations. So the point here was really that in the previous approaches, the two real symmetries that you might want to pose on a holomorphic vector bundle, they have a complexification, and the complexification of those fields has fixed points. And so if you try to go all the way down, quotienting this three-dimensional twistor space by two complex vector fields, you go down to a Riemann sphere, but you have to take holes out at the origin and infinity where the fixed points are, and the construction becomes singular. Okay, so this is then this kind of diamond of reductions as Middleton and Skinner introduced. So today what I want to do, though, is to focus on the self-duality. So that was all by way of preamble, sort of part of my own prehistory in the subject, and that of Roland and David and so on and so on. So what I want to focus on for the rest of today's talk is the Hitchin equations on a Riemann surface. So yes. Yeah.
Can all lower than models with
Okay, so the question is whether all 2D models. So there were some gaps in the story. So there are models with elliptic curves for their spectral parameter don't have a very nice description. By and large, we're talking about models that have a spectral parameter that lives on the Riemann sphere, but there are models. I think Landau-Lifshitz model has spectral parameter that lives on the elliptic curve, and that doesn't have a natural lift. You can sort of try and extend your framework so that it does, but it's less comfortable. And the other big gap in the story, maybe a bigger gap, was the fact that the KP equations don't have a natural lift to 4 dimensions. So the KdV, Boussinesq, and so on all do, but the KP equations don't. And what happens there is actually sort of worthy of a lecture in its own right. So just going back to my list of reductions here, what you see is that if you go down the self-dual gravity channel here, the dispersionless KP has a lift, has a twistor correspondence and a life inside the twistor framework. If you want to lift dispersionless KP to full KP, what you end up having to do is you have to do some kind of quantization. And so you have to resort to a non-commutative story. And this has recently been done by Roland Bittelson and David Skinner. So I sort of feel that by stretching the framework in rather a natural way, which is to go up through the self-dual gravity track and to sort of do some deformation quantization, you can get to KP. But the question of replacing the spectral parameter by a variable on the elliptic curve is slightly harder, but you can do it. We did write a paper on it, but I didn't like it very much. I didn't feel you were learning anything from it. Whereas I think you do learn something from the KP story. Okay, so the self-duality equations were presented as self-duality equations on a Riemann surface, precisely because what Nigel was doing back in 1986, so 40 years ago now, was to take self-duality in 4 dimensions and reduce it down to 2, just with straightforward translations. So in some sense, this is the generic reduction down to 2 dimensions. And you are, of course, left with a unitary connection on a bundle E in the 2-dimensional slice, but then the components of the connection in the two symmetry directions, they can be combined together to form a Higgs field. And it turned out to be natural to actually sort of multiply them by dW, where W was the remaining complex variable. So it became natural to think of the two sort of Higgs fields in the symmetry directions as having a life as a complex Higgs field in 2 dimensions times the 1/0 form, which we call var in LaTeX. And then the self-duality equations reduced to these equations here. You get the nice thing about writing the variables in this way is that the this curly phi is d bar closed, and then the curvature of this connection is given by the commutator of phi with its Hermitian conjugate. And you obviously also get a reduction of the lax pair from 4D to 2D. So these equations follow from the commutativity of this lax pair, which is now presented as a connection on the bundle E that depends also on the extra spectral parameter Z. So this then is a nice system of equations. So it's become extraordinarily important in recent years. So just to give you a list of applications. So maybe the thing that drives its importance was the fact that we started in life with a set of equations that was conformally invariant in 4 dimensions. And you'd expect the symmetry group of the reduced equations to have just the commutants of the translations, the symmetries that commute with the translation reduction. But instead, it becomes infinite dimensional. And so you discover that the equations are actually conformally invariant in 2D, and that's, of course, infinite dimensional. And so they only depend on the complex structure on the Riemann surface. They don't depend on the metric. And then one of the things that Nigel noticed was this, if you throw away part of the equation here, so this D automatically defines a complex structure on the bundle over the Riemann surface. And you can impose the condition that d bar phi is 0 without mentioning the rest of the Hitchin equations. And he then studied the moduli space of Higgs bundles. So in fact, I've sort of misstated it here. It's the moduli space of Higgs bundles. That's a finite dimensional space. It's very naturally the cotangent bundle of the moduli space of holomorphic vector bundles. The phi forms a kind of a natural 1 form in the space of on the moduli space of holomorphic vector bundles. So this is like the cotangent bundle of the space of holomorphic vector bundles. And so therefore it has a complex symplectic structure from that definition. And he then showed that this has a complete set of commuting Hamiltonians. And so it's a completely integrable system. And so that became a very intensely studied object. But more than that, so this amazing series of papers that Nigel wrote in the 80s, he showed that the moduli spaces of regular Hitchin systems emits not just this complex structure I'm talking about here, where you forget about half the equations, you think of E as a holomorphic vector bundle and phi as a section of 1/0 form sense of the bundle, endomorphisms of the bundle. But you actually have a hyperkähler structure on this moduli space. And the moduli space then, therefore, has a twistor space. So this is an extended version of the self-dual Einstein equations. And that in itself became intensely studied both by pure mathematicians. So it provided the arena for geometric Langlands program, which is still very busy, although sort of it's being cleared up slowly by the pure mathematicians. Higher Teichmuller theory, so these moduli spaces have Teichmuller components. and they have higher type Muller components that are quite mysterious still. But also the physicists got very excited. These equations arise very naturally when you're sort of dimensionally reducing from your 10-dimensional sort of, you know, down to 4 dimensions. And in particular, they play a key role in supersymmetric gauge theories in 3 and 4 dimensions. And in fact, my recent interest was sparked by some oldish work of so you know, in the book we had various we used the Hitchin equations as a starting point to do symmetry reductions to sine-Gordon, Toda, sigma models and harmonic maps. But more recently, I think it was observed by Pohlmeier reduction that the Hitchin equations provide a natural starting point for the study of minimal surfaces in ADS3 and ADS5. And so I haven't cited it here, but that's work of Alde and Maldacena from the 2008 to 10. And I was kind of, I got interested in this story again, and was interested in trying to quantize the Hitchin equations, but then discovered that you know, so this was the Alde, me picking up after rather late on the Alde Maldacena story, despite the fact Alde is 2 doors down from me. There's what structures that Alde and Maldacena were talking about were really, in some sense, Hitchin systems, or at least with partially reduced. And yeah, so then I was sort of a bit stymied by this usual sort of issue that I was talking about, that the quotienting of the twistor space by these symmetries, by the complexified versions of these symmetries, it meant that the twistor description wasn't very comfortable. You have these singularities. But then I also discovered that there wasn't really a formal 2-dimensional Lagrangian for the Hitchin equations in the literature, as I could find. Somebody in the audience will stick their hand up at the end and say, by the way, did you see this paper? But by then I'd learned about the 4D Chern Simons story. So this is an opportunity for me to sort of try and figure out how to do that. So I asked Kevin, he said, oh, nobody's done it. And Kevin Costello and Roland. And so I sort of teamed up with Roland, and we decided to try and do a 4D Chern Simons version. So, okay. So the 4D Chern Simons story is by now quite well established. But just to summarize, so the basic idea of it is that you use the fact that you're expressing your integral system in terms of its lax pair, and the lax pair is a 0 curvature condition, and the theory of 0 curvature conditions is the Chern Simons theory, is Chern Simons. So that was basically the starting point for Costello and friends, and so the theory encodes sort of the whole lax pair on the 2-dimensional Riemann surface, sort of, so to speak, the space-time, the space on which the equations are defined, Cartesian product with the spectral parameter. But in this story, we want to think of the spectral parameter differently to the to sigma w, the Riemann surface, in the sense that you want to think of this as being a complex manifold, and whereas to start off with, we're thinking we've got equations both in W and W bar. W and W bar are somehow symmetrically displayed in the Riemann surface. So it's often known as the topological plane, although it does have a distinguished complex structure in this story. So the lax pair then is a connection on a vector bundle over this 4-dimensional space. And but to encode the fact that this CP1 factor is a holomorphic, thought of as a complex manifold, we're going to have a meromorphic one form on the Riemann sphere factor. And it has to be meromorphic because the canonical bundle, the bundle of 1 naught forms, has degree -2. So omega has to have at least 2 poles. That's a standard fact of complex analysis. So here then, if we think of the lax pair then as this calligraphic A connection on a bundle E over this 4-dimensional space, then it's clear that this Chern Simons action will deliver that integrability. And so you get the field equations that F wedge omega equals 0, and we'll get a flat Z-dependent connection on the Riemann sphere. And furthermore, the fact that omega, wherever it's gone, this omega is a multiple of dz, it means that you can forget about any dz components in A. It's really a partial connection that only has dz bar, dw, and dw bar. It only really has 3 components. So in the Hitchin reduction, then we're just going to use omega is dz over z. And but as I say, we have a pole that the way I've written it here, z equals 0 and 1 is infinity. And so we're going to have to find some way of dealing with that pole. I should say that we've assumed that this bundle is going to be holomorphically trivial on the CP1 factor. That's a generic statement if its Chern class is trivial in the CP1 direction. Okay, so how do you deal then with these zeros? So that's going to be a key question. So, sorry, these poles in omega. One of the problems with the pole is that when you do a gauge transformation, a pole in complex geometry behaves very much like a boundary condition. And the reason for that is that if you take d of omega, that's really like d bar of omega, and that will give you a delta function at the origin. In complex analysis, you use the word residue. And so the variation of the action then gives you a non-trivial residue under a variation. And if this is a gauge variation, this will depend on the gauge choice at z equals 0. So you can think of this as a kind of really a classical gauge anomaly, and you have to impose boundary conditions that remove it. And there's actually a large number of choices that will remove this, this potentially anomalous term. And one way to say abstractly what those choices should be is that if you do the second variation, then the connection A should be in a Lagrangian subspace for this skew form. And so Costello and Yamazaki already set up a theory of those that give rise, that operate when you have a double pole. For the form that I'm talking about, dz over z, so they just said that A should vanish at the pole with a double pole. But for the form that we've only got 1 degree of vanishing rather than 2, so we can only really set 1 object to vanish. And the way that we do it, in fact, is, well, you can do it by, what you'll only ever see is AW wedge AW bar. And so what you have to have is that the product of these 2 vanishes to order 1 in Z. But this gives a hierarchy of possible boundary conditions. And so you can have AW bar vanishing very fast and AW more slowly, or vice versa. It's really just this product that has to vanish at order 1. And in fact, it turns out that if you want to land on the Hitchin equations, you'll take k equals 1 at z equals 0. And you take the symmetric thing at z equals infinity, but in this notation, at z equals infinity, it looks slightly asymmetric. But if you invert the coordinates, it's the same thing. And that's where this system learns about the complex structure, because we're making AW bar vanish to leading order at the origin, well, to second order at the origin, and AW vanishing second order at infinity. So it's this choice of boundary condition that's fixing the complex structure on what's otherwise often referred to as the topological plane. Okay, so that's how we deal with the boundary conditions. I haven't been looking at the time. I'm getting close to the end point. Okay, I better go faster, sorry. So then the theorem is there's some solutions to the 4D Chern Simons with these boundary conditions are gauge equivalent to the Lax pair for the Hitchin system. And the proof goes by saying that we assumed ab initio that these bundles were going to be trivial at the Riemann sphere. So we can find a trivialization which is holomorphic. This sets the AZ bar equal to 0. And if we do that, though, what we find is that the new A doesn't satisfy the boundary conditions. But we can sort of correct it. So it deviates from the boundary conditions I imposed on the previous slides by 2 components at the origin and 2 as infinity. So we can correct it by those 4 components to make sure that it does, to form an A prime. And then these are actually holomorphic in Z. And so A prime is holomorphic in Z as well. And the boundary conditions together with Liouville tells you that this A prime actually vanishes. So this AF then is equal, A prime vanishes, AF is equal to this, and I've written it in such a way that hopefully you can recognize it as the Lax pair for the Hitchin systems. And this F is unique up to sort of functions that are independent of Z. So this reduces now to the standard gauge we expect on the Riemann surface. Okay, so that gives you the fact that the space of solutions is the Hitchin equations, but we'd like to get the action as well. So you can start off in 4D. You can use this F that we used, but in order to do the correction, we've got to sort of get a bit more data about what it does by expanding in Z near Z equals 0 and infinity. And so we need the first 2 components expanded, F naught and F infinity, and then the order Z or one of the Z terms. And if we do that, then we can relate the F naught and F infinity and Z bar to the A and A's and phi's. And so you discover that the phi's are given by the derivative of these psi's, these components in here, and that the A in this kind of holomorphic gauge now is given in terms of H, which is F infinity inverse F naught. So this gives you all the data for the solution in terms of H and psi's, which are potentials for the Hitchin data. We can now substitute that into the action and reduce the action. And what we end up with is this. We sort of well, so as it stands, it looks a little bit messy. We've got a term which looks like a harmonic map into the H matrices, and corrected by the psi and psi tilde terms. And but we also get a F inverse dF cubed. So this ends up giving you a WZW term for the H. And just to sort of gather all the pieces together, you end up with a 2-dimensional action expressed in terms of the Hermitian metric on the bundle, whose Chern connection gives rise to the connection that we first thought of. And that is subject to a West-Wiener-Witten action. So that's this familiar form with the harmonic map plus the West-Wiener-Witten term. And that came out of the cubic term in the Chern Simons action. And then we get this term here, which, if you impose the field equations, is simply the norm of the Higgs, the L2 norm of the Higgs field in the Hermitian metric. And so, in fact, this is what Hitchin uses in his existence proofs for the solutions of the Hitchin equations. Okay, so we get a nice new 2D action. So I was interested, sorry, I just pause there for any questions. I've probably only got 10 minutes left, have I? Yeah, thank you. I've been saying too much. I've got, anyway, okay. So the, so I was saying that it was already well known that the Hitchin system sort of reduces to extended Toda and Shine-Gordon, just with some Zn reductions here. This is a familiar thing that you can find, at least we had it in our book, and I can't remember where we got it from. But if you impose this Zn symmetry, which also acts on the spectral parameter, then so starting in 4 dimensions, you're just imposing a discrete symmetry in the ignorable in the plane in which you had the original translational symmetry, and this forces the psi and psi tilde to be have this kind of mostly upper triangular or lower triangular form with the exceptional terms there. And we end up with the Toda equation, or at least these conformal Toda equations. You end up with this extra functional degree of freedom. And this was sort of, therefore means that we can also deal with these minimal surfaces in ADS 3 and 5 with. So that was So one of the things I was interested in then was to understand, so if you wanted to start thinking about quantizing things like these minimal surfaces in ADS, you might then start to worry about the symplectic structures and Poisson structures. And of course, Chern Simons makes that very easy. If you just do a canonical reduction on Chern Simons theory, you find that the symplectic form is essentially just the variation of A wedged to variation of A. Here, we also have to wedge against this holomorphic 1 form because it's a 4D Chern Simons. And so this gives rise to a so this is meant to be integrated over a 3-dimensional hypersurface. So you imagine doing a space and time decomposition. Here, that's slightly sort of awkward because we're thinking Euclidean. So sigma W is sigma plus I tau. You could analytically continue so that so tau goes to I tau if you wanted to make this Lorentzian. And there would be choices that make that all make sense. And so then if you maybe just to make things kind of a bit more concise, in that world, you'd let the sigma take values on a circle inside the Riemann surface, and then, or you know, think of the Riemann surface as a cylinder, and then this would essentially provide a symplectic form on the lax by integrating over this hypersurface, and that would be conserved by the field equations. And this gives rise to something which is easily seen to be what you would expect coming out of the action. So this is where H is canonically conjugate. So H is satisfying a kind of a sigma model action. It's a bit like a wave equation. So H is canonically conjugate to the tau derivative of H. And the potential for phi tilde is canonically conjugate to phi. So this is what you'd expect from the 2D action. And you can also show that with the Toda reduction, this gives rise to the standard symplectic structure on Toda. If you want to apply integral systems law, you can express this in terms of R matrices for the Poisson brackets of the lax. And ChatGPT was explaining to me that Benoit had already done this in some generality. So, well, I had to go to Benoit to find out which of the many papers of his that it had cited was the one. So it's a Benoit on his own 2021. So he has off-the-shelf 4D Chern Simons R matrix. And in our context, you can write it out in this way, where the Poisson bracket is given by some R, but you also get this extra non-ultralocal term, this so-called MyA term, which makes the kind of quantization a bit more awkward, or the Poisson brackets a bit more awkward to to use. But apparently in the constant case, that's sort of reasonable and works nicely. And so we get a nice simple form for the R matrix. And again, this can reduce naturally to give the well-known examples of TODA. So TODA provides a nice reality check on these things. Okay, did that just repeat? Okay, yeah, sorry. So then, the thing that was confusing was the fact Benoit also has many papers on the Hitchin system. The Hitchin system was this algebraic, completely integral system on the moduli space, and so these are R matrices for the Hitchin equations as a 1 + 1 dimensional field theory, but the Hitchin system is really a finite dimensional system on its moduli space, and so these were studied by Benoit and friends as well. They also have a treatment that comes out of this 4D Chern Simons story here, but with some adaptation. So on a compact, so just to be a bit more precise about the story, on a compact Riemann surface, the moduli space calligraphic M of solutions to Hitchin's equations is famously an algebraically complex integral system of real dimension 4 times the dimension of the Lie algebra, real Lie algebra times the genus -1. There are various games you can play when you've got other singularities. And I think I'm down to 1 minute, so I should be quick here. So Hitchin, back in the 80s again, it introduces a real symplectic structure on this moduli space, but it's also naturally a complex manifold, thinking of just the d-bar operator and the holomorphic Higgs field as holomorphic coordinates. And so this is a Kähler symplectic form for this, but he then also introduces a holomorphic symplectic form, which is given by this formula. And so altogether then, you have 3 symplectic structures which knit together to form a hyperkähler structure that's parameterized by some complex parameter in the Riemann sphere. And in order to access those from the 4D Chern Simons story, well, it only produces one symplectic structure. You know, it is a field theory in its own right. So the one that we first thought of then, the standard formula, that symplectic structure, works nicely to give rise to the omega I, if instead you choose your 3-dimensional hypersurface to be the whole Riemann surface, but now just with an equal time surface in the Riemann sphere, on the equator of the Riemann sphere. So that's one weirdness. And then, but then if you want to access the other ones parameterized by zeta, then you have to change your 4D Chern Simons theory and with it the boundary conditions. And just to say that you can also access the commuting Hamiltonians from the 4D Chern Simons perspective, because they invariance of this phi, which is just a residue z = 0 of A. So you can do it. So I'm still slightly unclear of the status of this, but that was what we put in the paper. So okay, given that I'm now over time, I think, or I'm now. Oh, I have 2 minutes. Oh, okay. So I can actually talk about my summary slides. Okay. Well, I could pause for questions as well. Oh, no. Okay. So okay, so summary and outlook. So, okay, so we've got a new 4-dimensional Chern Simons approach to Hitchin's equations. And this sort of fills in a gap in the Castello-Yamazaki sort of pantheon or and subsequent literature by people like Lewis and, well, sorry, there's plenty of others here who've probably written on this. And rather surprisingly, it gives rise to a new 2-dimensional action. And so what's weird in this story is that the symplectic structure from 4D Chern Simons gives rise to both something that works naturally as a 1 + 1 integral system of differential equations, but also in this 2+0 world by a different choice of initial surface. And one can do reality checks for at least the integrable field theory aspects of all of this by symmetry reduction to Toda and Sine-Gordon. Is that when I should start? Okay, I'll be very quick with the last few items. So there are various issues here. Globalization on the Riemann sphere is a little bit awkward. I mean, you know, there are various words we can say, and I still don't know in my own mind about this kind of squaring this different choices of hypersurface for the 1+1 versus 2+0. So if I was interested in the quantizing the string in ADS, in fact, it's really usually often thought of as a Euclidean world sheet, and then you know, is this really the right symplectic structure to be using to define the plus and brackets of a string on a string world sheet? So I'm still slightly unclear about that. And this point here is really where I was trying to go with this was to think about the ADS3 and ADS5 minimal surface problems and strings there, and to think about their quantization. This is largely because the this paper here, which was referring back to the Alde-Maldacena work, was really a story about strong coupling Yang-Mills, so amplitudes for strong coupling Yang-Mills, expressed as essentially semi-classical strings, so just ordinary minimal surfaces and their moduli spaces in ADS. And one would like to get beyond alpha prime equals 0 in ADS. So this is a kind of a long-term aim. And like many people, I prefer to study the easier problems of just, but I think the next problems are maybe going to be to try and understand this quantization. So I should stop there and thank you.
Thank you very much, Lionel, for the very nice introductory talk. Questions?
Thanks for the nice talk. Because you already have control of the Hermitian metric from Hitchin Simons, can you also see maybe something about the stability of the Higgs bundle? And maybe can you have like an alternate proof of non-abelian Hodge by Hitchin Simons?
Wow. Okay. So I think we're probably a little way away from that. It's already the case that we kind of left out the comments about globalization. We were really formulating things in a way that was certainly in the paper. We were just formulating things in a way that was essentially local on the Riemann surface. So one has to globalize first. That's not actually that hard, but we just didn't do it. Yeah, sorry. I somehow feel that the stability conditions and invariant theory involved. Well, yes, I'm sort of. I can't immediately see how 4D Chern Simons theory helps. I would imagine that one's probably going back to the sort of statements that sort of Nigel and Simon Donaldson and people already made back in the day about those. Worth thinking about those.
There is a question online. Okay.
Yeah, can you hear me?
Yes.
Okay. So a technical clarification and then a question, if I may. So with this new 2D action, you had a Wesson-Wiener term, a Wesson-Wiener-Witten term, and then the norm squared of d phi. Were these two pieces coupled or were they decoupled from each other? I couldn't quite tell.
So the norm of the Higgs fields obviously requires the Hermitian metric. So it's coupled in that direction. Yeah. So the first term doesn't depend on the Higgs field, but the second term depends on everything.
So that they're coupled through the stress tensor in the end.
Well, I mean,
through the metric coupling.
That's right. Yeah. So when you define the norm of the Higgs field, you need to know what the Hermitian metric is.
Very good. And so then the actual question. Wonderful to have this new 2D action. what do you want to do with it off shell that you wouldn't have done on shell before?
So I guess the image was more that well, I guess the first thing would be to actually see whether this action actually gives rise to the string action in ADS. That would be one thing to do. Another thing to do would be to just use it as a kind of a starting point for quantization on the world sheet. Although, of course, when you have an integral system, the real power of integrability is going to see how to translate that into statements about quantization in terms of the so to speak, scattering data. I mean, the data that defines the bundles and so on.
So maybe defining some exact test matrix or something.
That would be the hope. I mean, just to be a bit more concrete, what Alde and Maldacena did was that they encoded their problem in terms of what's known as a Y system. So the Ys were depend only on the spectral parameter, and various values of the spectral parameter they are just the standard coordinates on the moduli space. That they give rise to the cross ratios that define the boundary conditions of the minimal surface. But the Ys in this world were functions on the twistor space for the hyperkähler moduli space. So that was what was interesting for me, is that one would want to try and translate a quantization problem of the normal world sheet into something that you could express in terms of the Y functions and maybe their perturbations. So the Y functions are subject to a thermodynamic beta ansatz. One would want to know how to perturb around these classical solutions and set up some kind of quantum inverse scattering in terms of the Y functions.
Right. Yeah. Thank you.
Thank you, Dan, also. More questions? Yes, in the back.
Yeah, thank you for the nice talk. So a while ago, we derived a Lagrangian for these minimal these Toda systems that you get for these minimal surfaces in ADS5 and S5. Do you see any relation between your Lagrangian? I mean, you're probably not aware of it, so this might be an impossible question to answer. But do you see any relationship between your action and that action?
Sorry, which action?
So it's well, it's basically quite similar, but there's also a Liouville field appearing.
So I don't know if the Liouville field has anything to do with the FW there. So this is the conformal Toda story. Does the Liouville theory have some relationship to this extra conformal degree of freedom? So this is sort of a classic story that when you deal with these lax pairs, you don't get Toda field theory on its nose. You get this extra function of W, which you can get rid of with a coordinate transformation. But that will, of course, in general terms, destroy the global structure if you do that. So you don't necessarily want to do it. This F of W is, in some sense, a genuine physical degree of freedom, and it certainly is in the case of the minimal surface.
No, the action we get is sort of like G over G gauge Westermine or Witten, but then coupled to a term like the extra term that you had with psi and psi tilde, plus the Liouville field.
Okay, so I'm not familiar with this action, so maybe it'd be
we can just
helpful for me to see it, and yeah, it sounds very interesting. Yeah.
Maybe I can ask one question myself. It's a bit general. So you have this way of viewing two-dimensional integral theories from a higher point of view through Chern Simons, etc. Can you comment if actually for practical purposes, will you be able to compute things like beta functions or running of couplings, things like that easier or from a higher point of view, higher dimensional point of view?
Well, like all of these things, I'm sure you can do it both ways. I mean, you come up with a fancy.
It will give you new perspective, probably.
Yes, I think that's right. So for me, what I liked was the clarity of the kind of perspective that you get on the symplectic structures. That instead of getting some sort of fiddly thing out of a 2D action, which has different components going with different things, you have this straightforward sort of almost a tier bot form or something, yeah, so it strips away some of the complexity. That's not to say you couldn't do it the other ways. I mean, it's.
Thank you. Final,
Just regards to that particular question, then people in the audience have got handled Warburg, Sylvans, that's one person in mind, who have also showed that, in particular, if you're interested in the one loop RG flow, you can rewrite it in some uniform language in Chern Simons theory. So kind of the RG flow of the wide class of integral models can be rewritten as the flow of these the mark points that Lionel was referring to, sort of whole coherence.
yeah, I'm aware of this works, but probably I wanted to see if there's something more. Okay, thank you.